We know you've been waiting for this one. We've been playing around a bit and we're now going to show you the next step in our reaction sequence that started all the way back with white peppercorns. Just to recap, first of all we extracted piperine from white pepper using ethanol, and recrystallized it. We then took the piperine and hydrolyzed this in an ethanolic alkali solution to form piperidine, which we separated, and piperinic acid. So here's a couple of samples of piperinic acid that we've obtained. The one on the left is very clean and yellow colored, and originates from white pepper. The one on the left is slightly more brown colored and originates from black pepper. There's obviously still a little bit of the dark coloring that's made it all the way through the process. We're going to use the darker sample for this experiment, but there's really no difference. So here goes, our starting material, which is 3.7 grams of piperinic acid, prepared as per our previous video. It's lumpy looking, but it's quite a dry solid as you can see. Here's the chemical structure. What we're going to attempt to do is a fairly violent oxidation reaction where we'll try to oxidize the two double bonds in the side chain of the molecule, and the result will be various different products. However, we're hoping that one of them will be piperonal, an aromatic aldehyde. The first step is to get the piperinic acid into aqueous solution. To do this we're going to convert it into the sodium salt, which is water soluble. So here's 0.69 grams of sodium hydroxide. The same molar amount as our piperinic acid. We'll make these into a solution using a large beaker, which will end up being our reaction vessel. We'll need at least 700 ml of volume in here. And we'll use 100 ml of water to get these first reactants into solution. Use a large stirrer as stirring is important for the reaction. First we'll add the piperinic acid. As you can see, it's pretty much insoluble in water as it is in the acid form. So now we'll add the sodium hydroxide to the mixture. Immediately you can see the color change and the solids start to dissolve. Normally the solution is a yellow color, but we've obviously got dark colored impurities in here, so we've got a darker colored solution. Get the stirring up, and leave this for 10 minutes to make sure that everything has dissolved. The mixture goes a little foamy. If after a few minutes you've still got lots of solids, then it's possible your previous hydrolysis step wasn't complete and you've still got piperine in the mixture. This is looking good though. So the next step is to prepare our oxidizing agent. We've played around with a few things here and we've got a combination which gives a fairly low but reasonably consistent yield. So here it is. Double trouble. On the left we've weighed out 3.9 grams of potassium periodate, which is 1 mole equivalent. We prepared this in previous videos, starting all the way back from iodine, so go back and take a look for more info. And on the right we've got 5.4 grams of solid potassium permanganate crystals. This is 2 mole equivalents compared to the piperinic acid. Permanganate on its own can apparently be used for this reaction, but we've tried it and we get lower yields than with this combination. We think that these reagents work in conjunction to perform the oxidation process and break those two double bonds up. In the first step, permanganate reacts with a double bond, forming a diol as an intermediate. This will then react further with both permanganate and periodate to break and form 2 carbonyl compounds. Neither of these are very soluble in water, and in addition we want to keep the concentration of the mixture low in order to minimize excessive oxidation. So here's 500 ml of water at about 20 degrees C. Let's go. It takes a few minutes before the crunching sounds go away and we've got a deep purple colored solution. Okay, here we go. This is now ready to kick some double bond ass. We've got our 2 reactant solutions ready. We need to prepare one more thing though. One of the risks with this reaction is that the products, aldehydes, are themselves very prone to oxidation. So we need to stop the reaction after a period of time and quench any excess oxidizing agent. So we'll prepare a quench solution. On the left we've got 2.1 grams of solid sodium hydroxide. And on the right, 5.3 grams of sodium bisulfite, which is sodium hydrogen sulfite. We'll get these dissolved in about 75 ml of water. Together these will form sodium sulfite in solution, which is our reducing agent to quench the reaction. They dissolve easily. Note that we don't use sodium bisulfite itself to quench because although it would work, it could also react with our aldehyde product to form an adduct, which we don't want. Okay, well that's a lot of preparation for a reaction, but it's worth spending the time to get everything ready. Here's our 3 solutions. Let's start with our sodium piperinate solution in the large beaker. Just to help moderate the reaction a bit, we add 3 ice cubes to this, and start stirring. Stir the oxidizing agent solution with a glass rod and make sure that there's no solids settled on the bottom. And now with vigorous stirring, we add this to the piperinate solution. And we're going to wait now for 2 minutes for the reaction to proceed. You can see a color change starting to take place in the mixture, and a brown color forming. There's also a brown colored precipitate. Once you see this on the sides of the beaker, it's time to stop the party. Here we go after about 2 minutes. So now we add the quench solution. Pretty soon the mixture starts to settle, and you can see a light-colored solution with a fairly heavy precipitate in it. So let's start by filtering this and separating the filtrate from that precipitate. We first wash the precipitate with a little water. Then once it's relatively dry, we're going to wash it using an organic solvent to make sure that we've got any possible products out of here. We'll use 2 portions of 30 ml of dichloromethane, and wash the precipitate thoroughly with each one. We now take the filtrate and place it into a separating funnel. Hopefully it will just fit. There's a nasty black precipitate left in the filter, but we're not totally sure what it is. It's not manganese dioxide, so it might be organic byproducts or some other insoluble product. The DCM forms a nice obvious bottom layer. We shake the mixture up for a minute to allow maximum extraction, and then let it separate again. And we separate the bottom DCM layer. We do another extraction of the aqueous mixture in the funnel, using another 15 ml of DCM. Just to demonstrate, the aqueous mixture left in the funnel is still fairly alkaline. What this means is that any acidic byproducts, overoxidized compounds, or starting material from the reaction should have remained in the aqueous layer. Here's our DCM extract. We dry this using a small amount of anhydrous magnesium sulfate, and then evaporate off the solvent. Let's see what we get. We get an oily residue, which at room temperature solidifies and forms a beautiful crystalline mass. The melting point is somewhere just above room temperature, but we'll come on to this in a moment. It's all solid as well, with no oily component remaining. So enjoyed the view for a minute or two, and then broke up the solid and scraped it out of the container. It's quite solid and crystalline, as you can see. Not really waxy at all. And this is our crude product. 0.5 grams exactly of crude piperonal as a yellow-colored solid. This is a yield of 20% from the starting piperinic acid. Nothing spectacular, but it's the best we've been able to manage from this reaction. But it's still worth it. Why? Well, the aroma is simply incredible. The first thing that hits you is a wave of Jelly Belly toasted marshmallow beans. It's got that buttery richness to it, and it's slightly vanilla-like as well. But it's also got a fruity edge to it as well, like maraschino cherries. Overall, like a rich homemade cherry bakewell tart with almonds, vanilla, cherries, butter, and toasty aromas. Wow! And what's fascinating is having been through the process, first of all from the spicy white pepper, the fruitiness of the pure piperine, then to the relatively unscented piperinic acid, and now to this beautiful concoction. Okay, we know what you're thinking. Cut the poetic bullshit and show us some proof. Okay, here's our DIY melting point setup. Let's get some product in the tube, and a thermometer in there and set up. And we'll warm this now very slowly and gently. At 27 degrees C now. And the product in the tube is still completely solid. Getting up towards 30 degrees. And soon we've got our first sign that something is happening. There's some solid that looks wet on the side of the tube. And we've definitely got the start of a melting point range here. Temperature is 34 degrees C. And now it's completely melted. 37 degrees C. Well, the textbook says 37 degrees C for piperonal. That's pretty impressive. Our measurement is slightly on the low side, but it melts pretty sharply and it's very close. So ladies and gentlemen, this is the real deal. We're really pleased we did get a way to go all the way from peppercorns to piperonal. Even though the yield is not great, it's something we really hoped we could achieve and capture on film. There are probably other ways to do this, but copper sulfate didn't work for us, and plain permanganate was lower yielding and unpredictable. Stay tuned.